Okay friends, so now we'll see into questions from quantum, from mainly Slater's determinant, uh, as was the title says, perturbation theory and variational theorem. We'll mainly solve questions and also see some concepts as we go on. Okay, so let us see the first question. So it says over here that for a hydrogen molecule, the ground state function, okay, is psi12 is equals to phi12 and spin12, where psi12 refers to the space part and sigma is the spin part. Given that psi12 is equals to psi21, the form of sigma12 would be. So the first thing that we note from here is that uh, psi12 is equals to phi12, and because of which what happens is over here, right? So I'll just increase the thickness of this. So because of this, what happens actually is that we can say the space part is symmetric, and we know by the antisymmetric principle that the space part might be symmetric, but overall it has to be antisymmetric. Therefore the spin part needs to be antisymmetric, right? So this is actually from the Slater's rule, and I'll try to give you a kind of a detailed look into this. Just wait a moment. Okay, so you got it. Yeah, so we'll look into this Slater's thing in a bit of detail. Okay, so I'll just see what the answer is not mentioned over here. Let's see if the answer is mentioned. Yeah, C is the answer because this is like antisymmetric and this is symmetric. So let us look into the details of Slater's determinant. Cool. So as I said that psi has two parts. One is your spatial and one is your spin. Right? And actually the rule for this is that the spatial into, this is I think Pauli's rule, spatial into spin part has to be antisymmetric. So either the spin part has to be antisymmetric, this has to be symmetric, or this has to be antisymmetric and this has to be symmetric, because antisymmetric into antisymmetric is actually your symmetric, right? This is called Pauli's exclusion principle. So let us look into some cases for this Slater's determinant. Number one case that can be is when your helium is in ground state. So helium, as you know, has two electrons. So we have both of them in the same state, and for this actually there's a derivation. You need to don't need a whole derivation, but you just remember that for this psi is equals to 1 by root 2 phi 1 is 1, phi is 2, alpha 1 beta 2 minus beta 1 alpha 2. So main thing to note over here is that space part is your symmetric, your spin part is antisymmetric. Okay, So this is the case. For the second case, we will see when helium is in excited state. Okay. For this, what happens is that the chi. Okay. So normally in the excited state, whether of hydrogen or helium, what happens is that your spatial part is actually antisymmetric. Okay. Yeah. Yeah. So for helium in excited state, what we'll get is that chi will be your symmetric and your chi spatial will be symmetric. Chi spin will be your antisymmetric. Cool. And also for your hydrogen in excited state, what will happen is that your chi spatial will be symmetric and your chi spin will be antisymmetric. It's very easy to find out whether it's symmetric or antisymmetric. Just see the negative signs or not. Okay. And because the chi spin will be okay, what did I do? What did I do? Oh, I just messed it up. This will be the opposite case. In the excited state, what is happening is the chi spin will be symmetric. In the ground state, what was happening that the chi spin was asymmetric, but now the chi spin will be symmetric. Okay, because one has to be asymmetric to make the whole thing asymmetric, right? So this has to be asymmetric, and same for hydrogen as well. There's a big derivation. I'm not going into that. And see, when the spin part is actually symmetric, we actually get the so-called the triplet state, or something that has the spin multiplicity is 3, the spin is 1. So for these we can have something like alpha 1 beta 2 plus beta 1 alpha 2. Previously the spin was 0 and spin multiplicity was 1. It was a singlet state when it was asymmetric, right? But now it is your uh, what do you say, it is symmetric. That's why it's a triplet state. Okay. Great. And even hydrogen in the ground state, it will do the same. Hydrogen in the ground state, actually we looked at it. This is the hydrogen ground state, right? Hydrogen in the ground state wave function over here. So what is the case? As we have seen the case already, that spatial part is symmetric and your this part, what you say, the spin part is asymmetric. So that was it. So that was more of Slater's rule, and I think most of the things that come are within this only, the sphere of this. Okay. Okay, the second question is a very easy one. So I'm not going into the details of the second question, so it's very, very easy. Particle in a box of length, and it's given find energy difference. So that's very easy. I'm not going into the details of that. Okay, we have already looked into that in the previous video. You can see it. Okay, and last question, let us see. For the eigenstates of the hydrogen atom, which are the following relations between the expectation values of kinetic energy and potential energy holds for? So it's first saying for hydrogen atom, the relation between T and V. So there's a famous relation for this, which is called the, you might be knowing, it is called the Vedial theorem, right? So I'll tell you the details of this Vedial theorem first, and then we'll go into the other things, right? So let me tell you about Vedial theorem. Yeah. I took a different pen and explain this. Vedial theorem. So the main formula for Vedial theorem is this: 2T, which is the kinetic energy, is equals to NV. What is N? It is the homogeneity. Okay, I will explain this. This is one thing. Other thing to remember is that the total energy is T plus V, and potential energy is your 2E by N plus 2. Your this kinetic energy is Ne by N plus 2. Okay, so potential energy is 2E by N plus 2, and your kinetic energy is Ne by N plus 2. So now we'll come to what is N. Okay, so you mainly need this for SHO and your hydrogen atom. So for SHO, what happens is that your potential, is V equals to half kx square. For hydrogen atom, what happens is V is equals to minus 1 by your x square plus y square plus z square, or minus 1 by r square, actually you can say, right? So your homogeneity N is the your dd of x or r, as you can say, right? So over here x, so for this n equal to 2, and for this n is will be equals to, this will be actually whole to the power half. This will be n equals to minus 1, because square is getting square rooted, right? So it's minus 1. And as we know that your 2T is equals to NV. So for SHO it will be 2T is equals to 2V. That means T is equals to V. And for this, your kinetic part will be 2T equals to minus V. Okay, because for the hydrogen atom, actually I'm saying. So the SHO is for the hydrogen atom. That's mainly of it. And if we're told to find the energy, suppose we're finding the energy for hydrogen atom in terms of potential energy. So this will be 2E by N plus 2. So this will be like 2E minus 1 plus 2. So this will be minus 2 and minus 1. So minus 2. Sorry, this will be 1. Sorry. Okay, and your kinetic energy will be Ne by N plus 2. So that's will be minus E by 1. So this will be minus E. So the total you see 2E minus E, total is E, which should be the answer. T plus V should be equal to E. Okay, so that was visual system, and let us with this knowledge solve the question. For the hydrogen system, so it's given hydrogen atom over here. Okay, so the following relations between them. So as we said that 2T has to be equals to NV, and for N for hydrogen atom is minus 1. So 2T equals to minus V. This will be the answer. Okay, cool. Let us go to the next set of questions. Okay. The energy levels for cyclobutadiene are alpha plus 2 beta, alpha minus 2 delocalization energy, the molecule. Okay, so this is actually talking about our Huckel molecular orbital theory. So to solve this, we will need some concepts of Huckel MOT, and we will be seeing those concepts in right now. So Huckel molecular orbital theory is also a method that is used to approximate the energy for the system. And first we will see it for the ethylene molecule. So we have to remember the energy levels for each molecule. So as in the ethylene molecule, okay, this will have, so okay, what I'll do is, first you have to know, I'll tell you the concepts and then I will also tell you all the levels. Okay, so ethylene molecule, remember that it has to have two levels, these two levels, and this lower level will be alpha plus beta, higher level will be alpha minus beta. Okay, this is your HOMO, upper level is LUMO. Ethylene, as you know, this will have, you have to see the pi electrons. How many pi electrons? Two pi electrons. So okay, so now I will tell you the concepts behind Huckel emitting. First is your pi bond energy. Pi bond energy, that is given by ET, is actually your number of electron into energy of state where it is present. Energy of state, or the level where the electron is present, right? So for your, what we can say, suppose I just, let me increase this page. Yeah. So what we can say for your this ethylene molecule, right? Over here, for we can say that ethylene molecule number of electrons is 2, and G of state is alpha plus beta. Therefore, it equals to 2 alpha plus 2 beta. Now let us talk about the excitation energy. For this, your del E will be equals to E of LUMO minus E of HOMO. This will be equals to alpha minus beta minus of alpha plus beta. So this will be equals to minus 2 beta. Right, LUMO minus HOMO. Now in the high level is a, like, there's a minus sign between it. Like there's more antisymmetry to it because it's like high level, and the lower level has a positive sign. And the last part that we have for this is your pi bond formation energy. Pi bond formation energy, and that is the beta part of total pi bond energy. Okay, so as we say, if we are saying for your this ethylene molecule, we can say that the pi bond formation energy for this will be 2 beta, because 2 beta is the beta part of the total pi bond energy, right? So this was the main logic behind it. Now we'll see some structures and their energy levels, which is very important. Let me use a different color pen. Use the not the red pen, the green pen. Hmm. So first for cyclobutadiene. Okay, so cyclobutadiene, what happens is the lowest level is alpha plus 2 beta. This is your alpha. The highest level is alpha minus 2. So as I said, the higher level will be a minus sign, lower level will have a plus sign. This has a normal sign. And cyclobutadiene has this structure. So this has 4 pi electrons. So you 1, 2, 3 and 4. This is HOMO, this is LUMO. Now for an allyl system. There are normally 3 levels for an allyl system. Lowest level is alpha plus root 2 beta, then alpha minus root 2 beta. Allyl system can be of 3 forms. One is allyl cation, one is allyl radical, and one is allyl anion. For allyl cation, there are 2 electrons. For allyl anion, there are 3 electrons. For allyl like pi electrons, I'm saying allyl anion, there are 4 pi electrons. Okay, you have to remember, like memorize these levels. Okay, and now let me see. For your cyclopropenium ion, minus plus. Okay, alpha minus beta, alpha minus beta. So alpha plus 2 beta. Okay, so these are the levels for it. So that is in cyclopropenium ion. There are like 3 levels. One is the lowest level, which is alpha plus 2 beta, and the higher level is alpha minus beta and alpha minus beta. Okay, so there's no option but remembering these actually levels. Okay, we have to remember there's no option. So butadiene, let us see. There will be 4 levels and 4 pi electrons as well. So there's a trick of remembering this. This is alpha plus 1.6 beta plus 0.6 beta, alpha minus 0.6 beta, alpha minus 1.6 beta. And lastly for benzene. For benzene there will be, as you expect, there will be 6 pi electrons, 6 energy levels. So your number of normally you can say like number of pi electrons is actually number of levels. Okay, we'll see into that one more time as well. So lowest level will be alpha plus 2 beta, highest level will be alpha minus 2 beta, and these two levels in between will be alpha plus beta and alpha minus beta. So let us look into all the ones one more time. That in your ethylene molecule, what we said, there is a lower level which is alpha plus beta, higher level is alpha minus beta, and this is it, right? For your cyclobutadiene, can remember it? Try to remember it like I'm trying to remember instead of looking at it. Okay, because we have to remember all these things. There's 2 ways of doing it actually. So cyclobutadiene, there are 4 pi electrons, there will be 4 pi energy levels, right? And the upper ones will be minus, the lower ones will be plus. So if there has to be 4, like if the lower one is alpha minus 2 beta, if the lower one is alpha plus 2 beta, the highest one will be alpha plus minus 2 beta, and the middle ones will be alpha and alpha. That is the case, right? For allyl system, there are normally 3 pi electrons, there were 3 energy levels as well. The lowest level will be alpha plus root 2 beta, the middle level will be alpha, the highest level will be alpha minus root 2 beta, right? For cyclopropenium ion, there again, like you can say like 3 electrons. So the lowest one will be alpha plus beta, 2 beta, and the upper levels will be alpha minus beta, 2 of them. So for butadiene, you can say there are 4 pi electrons, therefore 4 energy levels. The lowest one will be alpha plus 1.6 beta, then alpha plus 0.6 beta, then alpha minus 0.6 beta, then alpha minus 1.6 beta. For benzene, there will be 6 pi electrons, 6 energy levels. The lowest one will be alpha plus 2 beta, then alpha plus beta, then alpha minus beta, then alpha minus 2 beta. Okay. So see if I can remember these things, you can also remember. Okay, so I'll just look into this one more concept that in sometimes it is asked that for the allyl level, okay, for allyl system, you have to say the three levels: the shy 1, shy 2, and shy 3. Okay, sometimes asked what are the energy levels for these. So actually for this, first one is shy, like half of phi 1 by root 2 phi 2 plus half of phi 3. Okay, this will be 1 by root 2 of phi 1 and minus 1 by root 2 of phi 3. The upper one will be your half of, this is actually sometimes asked that give the energy levels of this by root 2. Oh, I just messed it up. This will be shy 1. This will be shy 2. This will be shy, because shy 3 will have a minus signs, not the. Mhm. So a simple way of remembering this is that shy 1 has plus in between. Shy 3 will have minus in between. There is like two halves in the extremes and 1 by root 2 in between. And for the shy 2 one, there are only two energy levels and both have 1 by root 2 and minus in between. Shy 1 and shy 3. That's it. So that is more or less of it, and let us with this knowledge try to solve the question. So what it is asked over here, let us see. The energy levels of cyclobutadiene given, the delocalization energies. We want to ask the delocalization energy. Okay. So how to find this stuff? Okay, this is actually the most common question that is asked, that you have to find the delocalization energy of a system. Okay, and let us do this thing. So I did not give you the formula for finding the delocalization energy. I'll give it to you right now. So it is saying where did this thing go? Yeah, great. So let us do this. Yeah, delocalization energy. The total energy minus your energy of ethylene unit plus your energy of electron in pz orbital. So this is actually used, either energy in electron pz is used in your allyl radical or your cyclopropenium ion, as you can see. Okay, apart from these two, like this is actually taken as 0. So total energy, let us cyclobutadiene. So let us draw the energy levels. Right. So total energy will be plus alpha plus alpha. This will be 3 alpha plus 2 beta. This is the total energy. Energy of ethylene unit. For, if you remember, the ethylene unit was just alpha plus beta, alpha minus beta. Energy, there were 2 electrons, so this is like 2 alpha plus beta. So this answer will be 3 alpha. This will be 0 minus plus 2 beta minus of 2 alpha minus of 2 beta. This will be alpha. So this should be the answer. And your energy of electron in pz orbital, this is only, as I said, no, sorry for the spin marks. Energy of electron in pz orbital is if you have cyclopropenium ion. So let's first see the answer, whether alpha is as an answer given in this thing. No, right? I realized that it was doing some mistake, but I didn't realize where. Okay, I got the mistake. Okay. There's actually a concept that sorry for those pen marks. The concept that is the energy of the ethylene unit. See, in cyclobutadiene, you have to see first there are two ethylene units, so they'll be like multiplied two times. So these things will be multiplied two times. Okay. And for cyclobutadiene, as we can see from here, that see, when we find a total energy, we have to see the electrons as well. So in the lowest level, we have two electrons. So this will be 2 into alpha plus 2 beta. Then alpha, 1 electron over here, 1 electron over here. So total will be 4 alpha plus 4 beta. Right. And over here, this ethylene, there are two ethylene units, and uh, the energy of them is alpha. So this will be 4 alpha plus 4 beta. This will be also 4 alpha, 4 beta. So all will get cut. This will be equal to 0. And 0 is an answer that is given. Right. That is how it's done. Ah, I got an itchy nose. Ah. Sorry for that. So to explain this concept that I said one more time, like for the energy of electron in the pz orbital, okay, is actually, as I said, for your two cases. One is your cyclopropenium ion and one is your this allyl. So let us see for cyclopropenium ion. So there will be two electron in pi bond, one electron in pz orbital, and over here that is a two electron in pi bond and two electron in pz orbital. So as you can see, there are two electrons over here, two electrons over here, one electron in pz, and two electrons in pz only. Okay, so now let us, so you know this beta is also called your resonance integral, resonance integral. And now let us look into your allyl system. For the allyl system that we have, so if we are to find the, suppose the delocalization energy in the allyl system. So in the allyl system we have only one ethylene unit, total energy. Suppose we are finding it for your allyl anions, there will be 4 electrons but only one ethylene unit. Total energy will be 2 of alpha plus 2 beta plus 2 of alpha. Energy of ethylene unit will be energy of ethylene, there is only one ethylene unit, right? And ethylene unit has this like alpha plus beta, alpha minus beta will be 2 electrons. So this will be your 2 of alpha plus beta. Done. And these two having said, you have to say the energy of electron in pz. In pz, how many electrons are there? There are 2 electrons, right? And for this energy of electron, this what is the formula is the number of electrons into alpha. So number of electrons is 2 and it will be 2 alpha. So now what we will do is the answer for this will be your 2 alpha plus 4 beta plus 2 alpha minus 2 alpha. So this is the your ethyl unit, that right? Minus 2 alpha minus 2 beta, and this is the p orbital unit, that is minus 2 alpha. So 2 alpha, this is 4 alpha, which gets cut. This will get cut. So answer should come as 2 beta. Okay. Okay, again I made a mistake. Oh no, I'm making bad mistakes again and again. So see, so the lower part was actually alpha plus root 2 beta, not alpha plus 2 beta. Yeah, this was a mistake I made. And apart from that, it's all right, right? So when we are actually multiplying this, this will be your 2 root 2 beta, and this is 2 beta. So it will 2 beta root 2 minus 1. So this is the answer. You find it out, and this is the answer. Okay. So this was to explain this part. Now let us go to the next question. It is saying that the certain particle encountering a barrier, the tunneling probability is approximately e to the power minus 10. The mass is halved and the width of the barrier is doubled. The approximate value for tunneling probability will be, okay. So what is given in the question? Let us see that again. The pen, oh कहाँ गया? Yeah, there's a barrier. Tunneling probability is given. Mass is halved. Width is doubled. The value of tunneling probability. So see, there's a formula for tunneling probability. It's given by this. T is equals to e to the power minus 2 2m into e minus v by h cross l, where E is your energy, V is potential, m is your mass. H cross is Planck constant, L is the length of the barrier. Over here, you don't need to know any values because no value is given as such. Just mass is halved and width of barrier is doubled. Okay, that means that your m is equals to m by 2 and L becomes 2L, right? And just replace these values, then you have to divide it, like take the ratio out of them and find out. So let me do this part. So tunneling probability, let me use a different pen. That, okay, I can use different color pen also. I will use this color. This is equals to e to the power minus 2 root of 2m e minus v, where m is mass, by h cross into L. Okay, this was the formula, right? Yeah, it is formula. So now they are saying that m is equals to m by 2, L is equals to L. So this is T1, this is T2 will be equals to your e to the power minus 2, m is equals to m by 2 e minus v by h cross 2L. This gets cut, 2L. There's a 2 outside, right? And for this we can say, if we are taking this out, we can say that there's a root 2 outside, and for this there's a 2 outside. So if we say T1 by T2, this will be actually equal to your e to the power this will be, so we can say e to the power minus 2 Okay, and we can take this part common. We are taking this part common, m e minus v by h cross l, and this will be root 2, and so actually this was also minus, right? It is a minus. So when it got above, it became plus, right? It became plus. So this will be root 2 plus 2. Yeah. And this is given as e to the power minus 10. And this value is actually, this value is actually 1.44 plus 2, that is 2 point, this is 3.44 into this. So into 10, this will be e to the power minus 34.4. Let us see if this is the answer given or not, something like that. Okay, they're given the answer in this form. Did I make any mistake as such? Let us see the solution once. So what is the question actually? They are saying the mass is halved, approximate value of tunneling probability will be. Because the exponential does not get multiplied, right? When we are dividing two exponentials, those will be, but okay, I understood now that see, this will be, so if we have to find the value of this, so what we can do is we can actually say like there's a root 2 over here, so we can say this is root 2 and this is again root 2, and this whole part is actually e to the power minus 10, and this is your root 2. So because you don't have to compare, we have to just find the energy, so it's minus root 10 into root 2. This will be the answer. That is the answer that is given. This one. Yeah. Great. So this is about Hermitian about the last question. A is equal to minus dx plus x. Which one of the following statement is true? Okay, Hermitian operator actually is, I mean, what to say. We are not actually doing Hermitian operator in this part, but this is actually very easy. Okay, because if you know it from beforehand, there are some rules and things to it. So we won't be solving Hermitian in this portion, but maybe in the next portions, because we are actually solving the only approximate methods that are coming. But I'll solve it in the end. If we have time, we'll solve it in the end. Okay, let us see this first question that I want to see. First question says the average value of radius r in the 1s state of the hydrogen atom. Oh, I told you the formula for this. It's a very big formula. It's given in the lower part of the page. Okay, it's n squared a0 by z and into 1 plus half 1 minus l into l plus 1 by n squared. Okay, it is given for like 1s state. Let us try to do that. If I'm not wrong, the 1s state is actually a very famous one, which comes to 3 by 2 a0. Actually, this you can remember. The 1s state is comes to 3 by 2 a0 always. So this is very it's only 1.5 actually, but I'll just show you how it's done. And this is a very famous 3 by 2 a0 for the 1s state. It's a very famous consequence. So the average of r is equals to n square a0 by z 1 plus half l into l plus 1 or minus 1, minus 1 I believe, by n square. Just let me again check this because it's such a big formula. Okay, it's 1 minus l into l plus 1 by n square plus half, so this will be 1 minus, let's just grab the eraser, where's the eraser? This is 1 minus, it's saying for 1s, n is 1, s, so l is 0, L is 0, this whole portion 0 into 0 minus 1 is 0. N is 1, this is 1. This will be A0, and for hydrogen Z is equals to 1. 1 plus half N square 1. This is 3 by 2. 3 by 2 is 0. We got the answer. Okay, so other questions are from the degeneracy and stuff. We did this in last class, so we won't do it over here. Let us see the next part. The first one we actually have leave. 4. Well, let us just see this question first. Using Huckel molecular orbital approximate 2 roots of cyclic equation of ethane. We told you, right? Alpha plus beta, alpha minus beta. So this is the answer. C1. We're done with this. So this part we also have done, like number 6. It says that energy of harmonic oscillator in ground state is half H cross omega contributed to average kinetic and potential energies. Great. It's given as half H cross omega. Let us do this one. So energy is half H cross omega. And here it's saying find energy of the potential and the kinetic. This is the total energy given, and this is for SHO, right? Yeah, harmonic oscillator. So for this we know that the formula is 2T equals to NV, and for your harmonic oscillator N is equals to 2, so T is equals to V. And so what we have to find actually, we have to find the kinetic and the potential energies. So that is easy. With the whole, this is the whole E. We know T plus V equals to E, and in this case we know that both are same, so we can say T plus T equals to E. So 2T equals to E, that means T is equals to E, that means T is equals to 1 by 4 H cross omega, that means your V is also equals to 1 by 4 H cross omega. Is this the answer? Yeah, first one only. Done with this. Okay, energy of hydrogen atom in this okay, we actually did this. Actually, I mean, actually like showed how to do this in the previous class, but I'll do this again. The energy of hydrogen atom in a state is minus 8CRH by 25. The degeneracy of the state will be. Okay, so energy of the hydrogen atom is actually given by minus 13.6 Z square by N square, or it's also given by minus 8CRH by 25. So for hydrogen atom, Z is equals to 1, he's taken that, and this whole value is equals to minus 13.6. 25 is actually N squared, so N is equals to 5, and that is the degeneracy, that N is equal to 5. This is the answer. First question, now let us see, it's from perturbation theory. It says the following 3 statements of the perturbation theory, and which one is correct, right? It's saying second order perturbation correction is always negative. That's true. Second order perturbation is always negative. That is actually a very true statement. The sum of the zeroth order, the first order corrections out of the ground state energy is always greater than the exact counter state. Yes, because it's an approximate value. Therefore, sum of zeroth order and the first order is always greater than the sum of exact ground state energy. Yeah, sum of zeroth order and first order corrections to the ground state is less than the exact energy. So, no, that's not right. So A and B are right over here. Both A and B are true. Okay. So talking about perturbations, I'll just show you some formulas of perturbations. So you can just use, it's an approximation part to calculate the energy part. I'll just show you some formulas for the first order correction and the second order correction, for the perturbation energy. Okay. So the first order perturbation is actually given by del E equals to psi H I star and eta. Second order correction for the perturbation is given in the form of your. So there are different cases for like particles in a box or SHO, right? So we'll come into that when we actually, or should I say it right now? I think I should come into that when we have the questions ready. Second order correction is given by Cheyenne, del H, Cheyenne, and we have En minus Em. This is the whole square. Don't even worry about much about this because it's actually a pretty easy one. Right. Okay. Let us see some other questions. Trial wave function. Okay, this is on variational theorem. Okay, this is a very important, like a very interesting question. But okay, so this is from variational theorem. We'll do this first. Okay, great. So if you think last video, I don't know if it's uploaded or not, but I talked about a bit of variational theorem, and this is on secular determinant of variation theorem. So I'll just okay. So there are some values given, and it's saying the approximate ground state energy of the system is what, right? And over here also there are some similar things going on. Okay, so I'll just talk about variation theorem a bit, then we'll solve the questions. So variational theorem is nothing but a, let me take a different color, a good color. Give me some color. Let me take, which color do you want? Inky, pinky, ponky, not this one. Let's see how it comes out. Ah, very stupid. Uh, just take dark blue. Variational theorem, right? For this, the trial wave function energy will be more than the your actual energy, more. This is the main thing, that the trial energy is more than the actual energy. Okay, and now we'll see some aspects of variational theorem. So perturbation is not given, but I'll again teach perturbation as well. So okay, let me just take a small break and I'll just come back and teach both variation and perturbation. Okay, so now we'll talk about variational theorem. Great. Okay, so that was what I have said about variational theorem, and now the trial wave function. And normally what you do is you find the actual, suppose you're finding for a 1D box, so you just find the energy for the 1D box with the formula of n square h square by 8 ml square, and then you find the trial wave function is more than this, whatever n is, just put it. Now we talk about the secular determinant, which is also like a part of variational theorem. It is given by h11 minus es11 h12 minus es12 h22 minus es22, sorry, h21 minus es21 h22 minus es22. This is equals to 0. Okay, and normally your h12 is equals to your h21, s12 equals to s21 equals to 0, s11 equals to s22 equals to 1. Now having said all these things, let us see what the question was saying. Oh no, the question, it would open again that. So this is C. This is your h11, this is your h12, this is your h21, this is your h22. So we have all the values, right? We have the value of h12, 21, we have the value of h22, we have the value of h11. We'll just see the values of 1 and 4 the values 0, 2 and 3. Great. Zero, 2 and 3. So this will be 0 minus E and 1, 2 and 2, 1 will be 0, 0, 2 and 3. ES1, 2. This will be 0, right? Because S12. This again will be 2. This will be 3 minus E. Yeah. So this will be minus E, 3 minus E, 2, 2. And we have minus E, 3 minus E, minus 4 equals to 0. Minus 3E plus E squared minus 4 equals to 0. And we have E squared minus, okay, minus 4E plus E minus 4 equals to 0. Let's copy it down. E minus 4 plus E, what happened? E of E minus 4 plus 1 E minus 4 equals 0. So E is equals to minus 1 or 4. So let us see the answers. Was the answer given? Plus 4 or minus 1. So they're taking the lower value, actually minus 1. Okay, great. G plus 4 was also value given, so they have given an MSQ question actually. Anyways, next question also from variational theorem. One molecular orbital of polar molecules AB has form of this: Ca psi s, Cb psi b, where psi a psi b are normalized atomic orbitals and electron in orbitals is found on atom B with a probability of 90%. Neglecting the overlap between psi and psi b, calculate possible to Ca and Cb. Okay, so see over here what is given is probability is given, and over here we are told to find values of C and Cb. So probability is the total probability will be Ca square plus Cv square, if I'm not wrong. That should be equal to 1. and it says that Chi and Chi B on atom B. So your CB square is 90%, 0.9 we can say, right? So let us see that question right now. That it's saying that your CB square is 0.9, then your CA square has to be 0.1, right? Therefore CA will be root of 0.1, CB will be root of 0.9. This should be the answer. What is 0.9? So we can say actually this is like 9 by 10. This will be 3 and root of 10. I don't. Root of 10, man. For a calculator for that. Yeah, I have a calculator. So I'll just do root of 0.9 only. Okay, the root of 0.9 is actually 0.94. 948. So you can say like 0.95. And root of 0.1. This is 0.316. So let me see if I have done it correctly or not. 0.95, 0.316, D is the answer, right? Got it. Yeah, that's the right answer. Done. Question 7 is an important question. Just see into this. Look a bit carefully. In the, oh no. So it's between like covalent and ionic terms. It's like more of, it's a like advanced concept. Okay. The formation of hydrogen molecule from two hydrogen atoms placed at positions A and B separated by a distance RAB. Part of special wave function is given. Covalent term and is important as, okay, so we have to say it's a covalent term and ionic term. Okay. And when is R important? Okay, this is another question. I thought this is the only question. So we'll just solve the other question because these are easy actually. Single electron excitation cell aluminum cation. So I already told you about this Huckel molecular orbital. So we can do that. This is about angular momentum Ly. So angular momentum Ly is nothing but your there's actually formulas for this. I'll just do it in the next part. This is all the basic stuff. Okay, so I have not done the basics over here. It's pretty advanced of quantum mechanics. I'll just come to all these things. Let us do this first only. So this is given that Chi A, this function is given. So A is our first atom, B is our second atom, and what we know that Chi A over here is atomic orbital A, this is atomic orbital B. So this is the concept. If both 1 and 2 electrons are the same atom, that is, it is ionic term. And why is it this? Just wait, okay? Just wait a bit. Oh my goodness. Okay, so it says the orbital has two parts, spatial and spin, and spatial can be two types, covalent and ionic, right? For ionic, both the electrons has to be on the same atom. That was taken by the one orbital. Is the case here. For covalent, only one electron is taken and one, because covalent is like mixing, right? And ionic is like all the electrons going from one atom to the other atom, but covalent is like mixing of two atoms. And so over here, 1 and 2 denote the two electrons, and A and B denote the two functions, Right, covalent or ionic, the concept only applies when they are close to each other, and that happens in D. So why is D the answer? Because see, both 1 and 2 they are in like A, and both 1 and 2 are in B. So it's not like Chi A1 plus Chi B2. That would be like covalent because that's like mixing. But the overall like both electrons on the same atoms and both electrons in another atom. So it's like ionic. They have to be close, like to interact, right? Both in covalent and ionic. So D is the answer. Full of life now, full of passion. Okay, so for it's given for Huckel theory now. Cyclopropenium cation. So cyclopropenium cation is something like this. Cation. So there are two electrons over here. Energy of a single electron excitation. So let us do this. This is actually quite a good question because we didn't do the excitation part. It's nothing but the HOMO minus LUMO. So we know that for uh, this will be minus root 2 beta. So, and this is, as you said, this is for your cyclopropenium ion. So there will be like 2 electrons. So it's saying this will be LUMO, this will be HOMO, and the energy for single electron excitation will be LUMO minus HOMO minus root 2 beta, or you can say it will be like root 2 beta if you want to see the modulus of it, right? So it will be like root 2 beta. So let us see if the answer is matching or not. The root 2 beta is there. No, it's not there. What I went wrong? Energy for single electron excitation and cation. Okay, sorry, it's a cyclopropenium cation. So I was doing it for an allyl system. So this is not the case. This is for allyl system. This is right for allyl. Okay, nothing wrong for not an allyl. Cyclopropenium cation is actually this, and the levels are this: alpha plus 2 beta, alpha minus beta. So there are 2 electrons. This is your LUMO, this is your HOMO. Alpha minus beta minus alpha. So we have to just see the energy. No need to see how many electrons are there or not, which used to be do in the delocalization energy and the energy of the electron. So no need for that. Minus 2 beta. So alpha gets cut. Minus beta is 3 beta. So 3 beta should be the answer. So is 3 beta an answer? Yeah, it is. Done. So as you can see, these are all net questions. Pretty cool, huh? Full of life now, full of passion. So let us look into this for concepts of angular momentum. So if you just first say the concepts. Angular momentum. So your momentum Lx is actually equals to y pz minus z py. So it actually goes in this fashion, like x, y, z, right? Ly will be equals to z px minus y pz. Understood the fashion? So is y, it goes from z px minus y pz. Right, so tell me for Lz, it's very easy. See, Lz will be x, first will x will come, then py will come, then z will come, then x will come, xpy minus zpx. Okay, I made a mistake. Oh no. Okay, I made a mistake. It's not like this actually. So like Ly is zpx minus, so this is px, right? So another has to be py, and there cannot be any, this is y, so there cannot be any y term, so this has to be x. So this is like similarly for z, so that's the first will come is your L. So for z this is given, so first will come is your xpy is given. So how? Okay, lyzpx. Okay, so lz is given. So first x will come and py, then z. No, not z. This will be ypx. Okay, and if you are told about the commutator of lx ly, so you can remember like this, like ly, this formula. So first see which one is coming. So ly, first which is coming is z. So it will be z, and then you figure out the next part. So see, there has to can be only two terms. There has to be z and x terms, like both in the constant form and the p form. So first is coming z, so it will be px and minus of what are the remaining part. It will be like xp. That is inevitable, right? Now it's very clear, right? Similarly for lz, first you see which is coming. X is coming, so x then py, and what is left? The ypx term. So we just write that down. So you see some commutator relations. Lx ly equals to 1 h cross lz. Your ly lz is equals to 1 h cross lx. xyz yzx lz lx equals to 1 h cross ly. And also your L square Lx equals to 0, and your x to the power n comma p equals to n ih cross x to the power n minus 1. Your x to the power p to x comma p to the power n is equals to n ih cross p to the power n minus 1. Okay, so when is x to the power, so the n part will come out always, so it's 1 h cross ih cross to the power x to the power n minus 1. And when it is this, it is this. And when it is, you are in this form, suppose px comma x, so we have reversed it, so there's a minus sign actually, nothing as such. And x comma px will be ih cross. And your x comma py with some other dimension or whatever it is 0. So with this, let us solve the question that is given. So in angular momentum ly is what? So ly we learned that ly is equals to ly is equals to the cyclic rule x, y, z. So x, that will come first, then px minus the left part xpz. Px is what? Px will be z of, so see, there will be z first and then x. So this kind of y ly, right? So this will be the answer, okay, because z and then x, but I'll just show you how it is coming as well. So px is minus ih cross ddx, and right, minus x of minus ih cross ddz, and 1 by I is actually equals to minus I. So this will be by I, we can take common z of ddx, and so they have to get the minus I comes, so this will be minus, yeah, minus x of ddz. So this is the answer. Okay, we have done this. So I had told you that I will talk about Hermitian operators. So let us talk about that. So the other parts are done. So I'm just cancelling the other parts. Full of life now, full of passion. Call me by name. Okay, what is the Hermitian operator? First of all, an operator is given by this form. And the complex conjugate of this operator is given in this form. Hermitian is when both of these are equal, it is called Hermitian. It is called anti-Hermitian when there's a negative sign involved. That is the main thing of Hermitian operator. Having said that, we'll now look at some theories of Hermitian. Theories of Hermitian. We take this pen. It says first theory, the average value of Hermitian is real and the average value of anti-Hermitian is imaginary. Then again, the eigenvalue of Hermitian is real and eigenvalue of anti-Hermitian is imaginary. The eigenfunction of Hermitian operator having two different eigenvalues are orthogonal. Full of life now, full of passion. Very important, the example is this. So I'll just give you some concepts. So A Hermitian is given by A dagger. So A dagger of dagger is actually equals to the operator again. A B whole dagger. So Hermitian of the whole thing is B dagger, A dagger. It's like the inverse, right? And what else? So if suppose both A and B are Hermitian, then AB will be Hermitian if A comma B commutator is equals to 0. You know commutator is what? AB minus BA. Otherwise, AB is anti-Hermitian. The most important example of Hermitian is your DDX and your moment operator actually. DDX. So suppose it's like nth order. So if n is even and n is odd. If n is even, it is your Hermitian. If n is odd, it is your anti-Hermitian. So ddx is anti-Hermitian, but d square dx square is your Hermitian. So you know px is what? Minus IH plus ddx. Okay, and you know kinetic energy. Kinetic energy is what? Px squared by 2m. So this will be, kinetic energy is actually equals to minus IH cross whole square d square dx square by 2m. So this will be minus I square is I square, like plus I square which is minus 1. So this will minus h cut square by 2m d square dx square. Yeah, that's kinetic energy. What I want to say is that both of them have this ddx form. So this has d square dx form. So this will be Hermitian. This has this part which is your anti-Hermitian. Your I is also anti-Hermitian. So both will mix and give you a Hermitian stuff. You can prove that as well. Okay, and so over here it says which is like a statement is true, a Hermitian or a Hermitian A. So first of all we note that ddx is anti-Hermitian and your x is Hermitian and your A complex conjugate will be, I think there's a shorter way of doing this thing. Yeah, this is a good way of doing this. So if like this is Hermitian, then the Hermitian of this is like a dagger only. Right. And via this we can prove that. Okay, so that was more or less it of all the things that we studied. It's a big lecture from Hermitian and anti-Hermitian. Okay, try to prove this out. Okay, this was a shorter way of doing this. I think I'll just maybe show in the next form, but this is a good proof that was done. Okay, they actually did the whole thing of it. So over here what is given is that A is equals to minus ddx plus x and A dagger is given is equals to ddx plus x. A dagger and A dagger A dagger will be, so if it's Hermitian then A Hermitian should be equals to A. That means A Hermitian, whole Hermitian should be equals to A Hermitian. Right. And we can say that the A Hermitian is this. A Hermitian is So we have to prove that this is Hermitian, right? So if we actually take the whole thing on this, then we have to prove, and again A dagger A, so you have to take the whole thing on this and then you have to prove. Okay, that was more or less of it. I'm not doing this, so you can do it on your own. And if you liked it, okay, God bless all of you and do practice, and I believe you will also be victorious.